short, the shunt winding is parallel with the armature. So basically it's going to be like this. Shunt and this one is a BT, IL. I call this one also IS. I call this one I shunt. And this one is the IA. Right? We call this one cumulative. Let's put a dot here. Just to show it. So this one means current entering this point is generating, for example, flux this way, right? It is a cumulative. They should help each other, right? So should be the dot here or here? Left or right? Left. Why left? They should be the same. These two, they should be the same to help each other, right? So this one should be here. Now for both of them, the current entering to the point is going to generate flux in the same direction. It's a cumulative, right? Now the other one is going to be short shunt differential. How about this one? So the circuit is the same. The circuit is the same. And let's say we say the shunt is the main one, right? The shunt is not changing. So this one, this is the IS, right? Should be on this side, right? This one is opposite of this. You see the current is entering to the point for this one. For this one is leaving the point, right? The flux, this one is going. This is just a symbol they're showing. You know, when you see the books and those kind of things, you see, oh, so this one is leaving the dot. This one is coming to the dot. So this one is a differential, right? So the other one you're going to have is going to be long shunt. Cumulative. Oh, sorry, long shunt. This is long. So, where is the dot for this one? See, this is long. Means the series winding is in series with the armature, and the shunt is all over here. Right? Compare this one with this one. We got here. The series winding is on the right here, here's on the left. They call it long because all these things are in series together. So if this one is going to be cumulative, where should be the dot? On the left. Why? Because this one is coming to the dot, this one should go to the dot also, right? Now the differential should be very similar, just to switch the dot. This one is long shunt. This is the IS, right? This is the ISH. So this one, as I said, the shunt never changed, right? That one is the main one. But here, it should be, right? If you want to draw the circuit, for example, for this case, these two, they have the same circuit, you know, they are just similar. But if you want to draw this circuit, it's going to be what? It's going to be EA, RA, RS, RSH, VT, IL, ISH, IS, IA, and you can write the equation. I'm not going to go through this kind of thing, but you can write the equation. So the last topic I want to talk about is the motor stuff.
So between the cumulative and the differential right here, you just switched it out on the series winding. Why is it? Why don't they switch? Like, why isn't there a case of switching it out on the shunt winding?
This is a P shunt, and this is a P set.
Okay, so it's much larger.
This one is the main one. Okay, you don't change the main usually. The one is going to be a little bit additive or it's going to be a little bit differential. That one you change it. So in general, the direction of flux is going to stay the same. You get a little bit more or a little bit less. Let me talk about the armature reaction a little bit, very short. Just I want you to know because I mentioned it several times. Let's at least what's the armature reaction, and we'll go to the last topic. I will talk to you a few minutes about this one, and we'll finish. Let's say this is a DC machine. Right? We have this flux going this way. This is the main flux. I call it main flux. Right? Let's say we have three conductors here. Just want to see. See, I'm going to plot here. This is, I call this one PF because it's from my field, right? This is a PF. Right? And remember when I explained about the brushes here we had our brushes here, right? We said here we have the maximum voltage generation, right? Because the angle was 90 degrees. Here we have the minimum voltage generation is 0. And here, unfortunately we didn't talk about the commutator. And here is the best place to switch the brushes. You know, this one has two half a circle, blades. So basically, when you are, this one is moving like this. So when the direction of current is going to change, see? If you look at it, the direction of current is like this, right? It's going to be like this, right? Here the direction current is going to change, right? So if you are going to change, for example, this conductor was connected to this one from here to here, right? This is a 180 degree. And current is this much, right? Now you are going to go to another half, right? You are going to change the plate. So the best place to change it is here, because the current is 0, right? If I jump from this plate to the next plate, when the current is 0, there is no spark, right? But if I, for example, if I jump from the plate, at this point, still there is some current, right? See, I am here. I'm going to jump to the other one. I have to jump from here. This is a spark. Only can happen through the air, right? The best place, I didn't talk about commutator that much. The best place to switch between this place is here, because there is a 0 voltage, 0 current, right? That's the best place to switch. To turn off that switch, if you think about it, the one we have over there, the best place to turn off that switch is at here, right? Try this one when it's dark at home night, you know. It's a little bit dangerous today, I mean. If you can open the cover and do the switching when it's dark. So you'll see some spark. Why? Because no guarantee you are going to turn it off at this point, right? Maybe you turn it off at this point, maybe you have a circuit like this, see? Right? This is your switch. And you have, for example, your bulb here, and there is a source here, right? When you open here, this one, what's going to happen? There's a current in the circuit, right? And based on Kirchhoff's law, the current cannot go jump to zero. It has to find a path. You open this one, right? But still the current is going to go through here to get to this point, right? This is a spark. As soon as you have the current find a path through the air, is a spark. But as soon as we hit here, it's good. It's going to stop zero, right? But if the circuit was DC, what's going to happen? If the circuit was DC, current is like this, right? You never ever should do this. Be careful. If you do this one, we had in the electric machine lab when we were working, over there. I told you, we have all this banana fish, those kind of things. One of the students, for example, took the excitation field fish out. That's all DC. It's not going to turn off. Because there is no zero. And it was like a chewing gum. The spark was going like this in the air. You know what I'm saying? The DC is DC you have to be very careful. AC, you see a spark, because there's a zero here, boom. Then you get the zero down. That's the reason building the DC circuit breaker is much more difficult and more expensive than the AC circuit breaker. AC circuit breakers, because there's a zero, is much easier to build. DC circuit breakers are very difficult to build, especially high current, high voltage. Now, okay, so they say the best place to do this one is to change it here because the current is zero. Remember one of the bad things we said about the DC machine, we said these brushes? It's not possible to do perfectly here because of this armature reaction I'm going to explain it. So when there is a spark here, small. The good one they have is very small spark. Those spark is going to start to eat these brushes, right? It's going to fatigue these brushes, right? After a while, they're not going to work anymore. You have to go replace it. This is the part is very weak in the DC machine because of all those sparking. But if you design it the best, you can make the life longer, right? Now, why these things happen? The reason here, look at here, the reason here is the best place if this is the I don't want to go to the concept of winding, just I want to say very simply. This is a VF, right? We know the best place to switch the current is when you are 90 degrees, right? Because at this point, when I'm moving either this way or I'm moving either this way, right? I'm parallel with this field, right? There is no voltage, right? But think about it. If this one is somehow, this field is shifted like this, and you don't know. You think its field is like this, right? You have your field like this, right? So, oh, my field is like this. But something internally changed this one and made it like this, right? Still you're switching the current here. Current here is not zero anymore, right? Where the current is zero, go 90 degrees. The new place is here, right? The best place is here now. Now let's say how these things happen. I'm not going to explain how to fix it, just I'm going to explain the problem with you guys. Now, we have one main field is a CF, right? Now forget the CF, there is no field winding. There is this current, right? How about this current? We're going to rate, magnetic field also, right? Let's put the finger here. This one is going to be like this, right? How about this? And here is going to be like this, here is going to be like this, right? How about this one? The same thing. How about this one? The same thing, right? Let's put all of them together. inside this iron, right? When you are generating voltage and current, right? The current inside here is generating another field here, right? It's generating another field here. There is one here and then one here, right? So this one is going to be for this one. For this one, it's going to be down. Okay? For one side is up, for one side is down. Right? This one is much smaller than this. But I just show it here to exaggerate it a little bit. Now, what this winding is seeing, what field is seeing? The resultant of these two, right? So look at here. This is my new field, right? You put your brushes here. So hey, here is the best place. I'm going to put my brushes here, right? Right? But it's not correct now anymore. Armature reaction changed my field, right? So I have to put it here. If you can put it here, it's correct. To fix it, there are three ways. I'm not going to go to the other. They call it interpole, compensation winding, and third one is shifting. This one is easy, right? To fix it, what you can do? Shift the brushes. But what's the problem with that? These are, I think, mostly in the book. I'm not sure in this kind of thing. But can you tell me, one way is if I can shift my brushes here, problem solved, right? But what's the problem with that? One day I'm running my machine with 10 amps, one day I'm running it with 100 amps, one day I'm running it 50 amps, right? One day is this much, one day is this much, one day is this much, you know what I'm saying? It's changing. If I put this one here for 50 amps, when my current is 10 amps is not good. When my current is 100 amps is not good, right? So that's the problem with shifting the brushes. Another way to fix it is, this is the best one and the most expensive. Let's come with some winding here. Let's talk about it. So let's put another windings here. No, because I talked a lot about armature reaction and I didn't tell you what's that, you know, and I felt bad a little bit myself. So I'm saying, keep saying that things, but I'm not talking about it. They put some windings here. They call it compensation winding. This one, they are in series with armature. See, what current is going through this winding here? Armature current, right? They put it here. Let's say this tree, they were generating a field like this, right? They set those one to generate the opposite flux. How should they? I think it should be like this, right? If we put it this way, inside this one, by this guy is going to be like this, right? And this one should be in series with armature also, right? Basically, this one is going to generate the same field this way. These two, they are going to cancel each other. But you can see it comes at cost. To put this one here is expensive. It's expensive. They call it compensation winding. Another way to do it is a little bit not as good as this one. This is very efficient. This is very efficient and good, you know, dynamic, you know, because whatever current is going here is going to come here, it's going to cancel it, right? Another way is they call it interpole. See, they say this is the circuit of the machine. They put some winding here, and these are again series with the machine. So what is going to happen? Look at here. There's two small poles here. See, this one is generating this way, right? This one is going to generate field down. Again, the current going through this one is the armature current. They make them in series with the armature. So basically, this one also again is going to generate like here. This one generates flux this way. This one is going to generate flux this way, right? Against what was the armature, right? They call it interpole winding. Interpole winding, if you are going to give them the rank. The best one, compensated winding, interpole winding, and shifting. Shifting is not really good, you know, because it's just for one current. If you know